So directions here on this problem. We're supposed to be finding the intervals on which the following functions are increasing or decreasing. Then find any relative or local extrema, assuming there are any. We're supposed to show our work to support these answers. That's kind of where this chart setup is going to come in. That's going to help us organize all of our information here. But with what we now know about this first derivative test, how it applies to critical numbers, what I would do, I would start by taking the derivative of the function, and I would use that derivative to help me find my critical numbers. So here derivative is going to be simply 4x minus 4x cubed. To find my critical numbers, remember I explore basically two categories, one where the derivative equals 0, one where the derivative does not exist. And remember, with the does not exist side, usually we're looking for some kind of denominator here. I don't have a denominator here, so I'm not going to worry about the does not exist side. Just focus in on the equal 0 part. If you focus in on the equal 0 part, you take your derivative, set that equal to 0, solve. Got some factoring in order here, so take out the greatest common factor of 4x. Leaves you with 1 minus the x squared. That all equals 0. Could factor this a little further, or just go ahead and take my factors, each of them, set them equal to 0, and solve from here. If I do that, I've got 4x equal to 0, so x equals 0. 1 minus x squared, if I set that equal to 0, solving for x, we got 1 equal to x squared. Taking the square root here, and we're solving, got to remember you got plus or minus in your answer, so plus or minus 1 would be what x is when you take the square root of that 1. If the question was find the critical numbers, we'd say, all right, critical numbers, therefore C is equal to, we've got 3 of them, right? We've got -1, we've got 0, we've got 1. If that was the question, there's our critical numbers. And again, those critical numbers have to be in the domain of the original function. Now, whether these values we found here are in the domain of the original function or not, they're useful to us in helping us explore where this graph's going up, where this graph's going down, and where the potential local relative maxes and mins are. So that's where the chart comes in. On the chart, what we're going to do, we're going to explore some intervals of x based on these critical numbers that we found. We're going to have a column here devoted to our derivative, because we'd like to look at something with the sign changes there. That tells us something about the original function. In fact, since that tells us something about the original function, as we explore those sign changes, we can note what's going on with the original function. And finally, this last column, we can use that column to discuss any extreme points we have, any of this relative local stuff that we got going on. All right, to build our intervals, once again, we're going back to these critical numbers to assist. If we don't explore the domain of the original function and we just start at -infinity, we can build our first interval -infinity to the smaller the critical numbers that we found, -1. We can then pause at -1. In fact, we can note something about the derivative at -1. We know the derivative at -1 is 0 because that's how we found -1 in the first place. We continue on now, building another interval. We've got -1 up to the next smallest critical number we found at 0. You pause at 0. We can note the derivative equals 0 because, again, that's how we found that 0 in the first place. Okay, next we'll go from 0 to 1. We'll pause at 1, noting the derivative is 0. And since we've gone through all these critical numbers that we found, our last interval will simply be 1 to infinity. Okay, after we set up our intervals, what we can do, we're just focusing our attention right now on our derivative column, which means everything I do from this point forward in terms of plugging values in, I'm going to go back to the derivative right here to assist me. If I take a number on this interval, negative infinity to negative 1, something less than negative 1, so say I take negative 2. If I plug that into the derivative, what kind of value do I get back? Is it positive? Is it negative? That's what we're looking to see here. What kind of value do I get back? Positive or negative? Not a hard calculation. What do you get? Maybe it is a hard calculation. It's positive, yeah. You should find if you plug negative 2 in, you're going to get a positive number back. Okay, now, sometimes with these signs, there are patterns to them, but please be careful. Those patterns only happen when you have certain kinds of functions. I've got a polynomial function here, so there's probably going to be a pattern. As we explore other functions, maybe not so much. If you take a number now on this next interval, negative 1 to 0, so something between those two numbers, say negative 1/2, negative 0.5. If you plug that back into the original function, I'm sorry, not the original function, excuse me, the derivative, you should find that you get a negative number back. All right, continuing through the next couple of intervals here, selecting numbers on those intervals, plugging those into the derivative, something between 0 and 1. Yeah, 0.5. Take 0.5, plug in. If you plug into the derivative, you should find that you get a positive value back. From 1 to infinity, be a little more aggressive here. I'm going to take 100 now. If I take 100, I plug in to the derivative, I get a negative value back. So, what are all these signs telling me? Well, they're telling something to me about the original function. I know now, since the derivative was positive on this first interval, from negative infinity to negative 1, if I looked at the graph of the original function, I would see on that interval the graph's going up. It's increasing. Likewise, if I look at this interval, negative 1 to 0 on the original function, using what I now know about the derivative, since it's negative, the graph would be going down, be decreasing. And if we continue with that trend, I see from 0 to 1, derivative is positive, so the original function must be increasing there. And from 1 to infinity, derivative was negative, so original function, graph must be decreasing there. Okay, in terms of extreme points, it's kind of like each column, the column that follows builds off of the column before. If I'm trying to figure out my extreme points here in the last column, then I'm using the information from the column before, and I'm looking for changes in direction. I'm supposed to understand if the graph goes up, the graph goes down, then at that particular point where the direction change occurs, there is going to be an extreme point. If it's going up, if it's going down, there's going to be some kind of maximum occurring there. So I would say here there's a relative or local maximum. Where the graph decreases and then increases. If it goes down, it goes up. Change in direction there, there's a relative minimum. And once again, we got a change in direction here. It's going up, it's going down. If it goes up to down, we got another relative maximum. Now this is where you start getting a lot of information on this chart to organize, what's going on with the original function, as well as organize your work to answer the question. It's a little hard to see how certain things are lined up. Right? Understand this relative max is lining up with x equals -1. This relative min is lining up with x equals 0, and this relative max is lining up with x equals 1. The reason that's significant is because if we're going to talk about a max or a minimum value for a function, we need to know what the value of the function is at those points. So we still need to find this part. So if we're going to find this part, and this is a value of the function, well, just use my heading here at the top to guide me. I'm going to take these x values and I'm going to plug back into the original function right here. So if I take -1, plug back into the original function right here, well, what do you get? You get 1 back, don't you? Likewise, if I take 0 now, plug back into the original function, value of the function is going to be 0 there. And then take 1, plug back into the original function, well, we'll get 1 back again. So if we were to graph out the original function and analyze it, we'd know where the graph's going up, we'd know where the graph's going down based on the information in this column. We also know specific points where we would see relative maxes or relative mins. For instance, we'd have a relative max at the ordered pair of -1, 1.